Hello, and welcome to the midterm demo video for Group 10. Our project is the Automated Laser Cavity Mirror Alignment and Beam Profile Modulation System. The members of this group appearing in today's video are AJ DeSantis, Computer Engineering, Bryce Moon, Electrical Engineering, Nicholas Pinkham, Photonic Sciences and Engineering, and myself, William Bowman, also Photonic Sciences and Engineering.
So as you can see, this is our optical setup. We have our open cavity laser. This is the output coupler. Eventually we will attach the motors to this to change these knobs, but right now we just want to display the optics. So the laser then exits the optical coupler and hits this beam splitter, at which point it splits into two and enters the two optical subsystems, the power meter and the beam profiler.
Here's the power meter subsystem. We have our photodiode and resistor from which we're measuring the voltage produced by the photocurrent from the photodiode. Here is a red laser that has a wavelength of 650 nanometers, which is rather close to our maximum detectable wavelength of 700 nanometers. If we look at the voltmeter that is measuring the voltage across the resistor, we're getting a value of 72.9 millivolts. I'll say 73. So if we put 0.073 for our resistor voltage, the resistance is 100 ohms on the resistor. If we do some conversions, then we can find that the laser power should be close to 22 or 2.2 milliwatts. Here is a rather reliable Newport power meter that is currently measuring the same exact laser and gathering a value of about 2.27, which is very close to our expected value of 2.25-ish milliwatts, showing the accuracy of the power meter that we have built. Here's a blue laser of 400 nanometers impinging on the power meter. As we can see, the voltage, a voltage is being read, which indicates that the power meter is detecting that there is light on it. However, this unfortunately does not correspond with the power beat that is measured by the Newport power meter when I test that, which indicates that the power meter can detect that there is light on it, which is good for the application. However, it is not an accurate power meter in that it cannot give a accurate reading of wattage at this wavelength yet. That is something that will need to be worked on for the final project, for the final demonstration.
So now I'd like to give a quick example of the Beam Profiler software running. So to start, it imports an image taken by the Raspberry Pi camera of the beam that's shown on the left. And then it does some simple image processing techniques such as converting it to grayscale and binarizing the image in order for further processing techniques to be done. Using the computer vision software library, I'm able to determine the vertical and horizontal image moments. I then use these to determine the centroid. I also use a built-in computer vision library function to determine the location of the maximum intensity pixel. From the centroid, I then scan the image vertically and horizontally to determine where the pixel corresponding to a 1 over e squared intensity is. This defines the beam radius in terms of 1 over e squared in both the horizontal and vertical directions. I then have a prompt asking if a focusing optic has been used in the system. If the response is yes, the prompt then asks what the laser beam's wavelength was. From this, it runs a couple calculations to determine the beam divergence and m² factor. After all these relevant calculations have ran, the program displays the image again. However, now the image is marked with the maximum intensity pixel, the centroid, and the beam width in the vertical and horizontal directions. As well as this, it also prints all the relevant parameters it has determined. So let's run this on this image and see what we get. We're going to say yes, and the beam is at 680 nanometers. So this is the processed image. We have the radius marked, vertical and horizontal. This green dot is the maximum intensity pixel, and this blue dot is the centroid. And as we can see, we're given a lot of important parameters such as beam diameter, divergence, m-squared factor, the location of the centroid and maximum intensity pixel, and the relative shape of the beam as well.
For this portion of the demo, we will be showing the electric motors and how they will react with the power meter. At the top is the power meter seen from previous parts of the video, which is connected to Pico via 2 analog inputs. At the bottom are the 3 motors. Motor 1 and motor 2 are used to adjust the knobs on the mirror stand, while motor 3 is used to adjust the stand itself. Here is a sample of how the motors should interact with the power meter. For the motors that adjust the knobs, we have found a basic design that will allow us to keep the motors in place while we adjust the knobs. While for the motor that adjusts the stand, we are still working on designs that allow us to rotate the stand while keeping it in place. Playing a video, we ideally would have the 2 knob motors move in increments, while the bottom motor will adjust the stand every once in a while to check for a lacing state. This process will be repeated until the lacing state is found. As seen, once the power meter detects the lacing state, the motors will stop. And ideally after this, the motors will then switch to a more sensitive mode that will allow us to find the max lacing state. And this process will be repeated until the results are found. Working on a project, we come across a few setbacks, one of which was that the 2 knob motors did not work in the rated voltage range listed on the website. To find that range, we bought a voltage converter that could convert 6 volts into whatever voltage we like. However, that voltage converter broke within the day and can only convert 6 volts to 5.6 volts now. However, we believe that the motor should work optimally at 4.8 volts. Besides that, we believe our main objectives now is to implement the PCB board and to create the mount for the board and the motors.
I'm going to go over the progress of our Q learning algorithm program for our project. Some things will be different in the final version, and I will go over those as I go. So first off, the dimensions of the environment will be the range of positions that the motors can turn. The actions will be to turn either one motor clockwise or counterclockwise, or the other motor clockwise or counterclockwise. The rewards will not be hard-coded into the program. Instead, they will be derived from the output of the power meter. And the rewards will be negative values because you don't want the actor just moving on random paths, just accumulating reward. You want it to try to take the shortest path. Moving on to the functions. These first 2 functions are just helper functions for the current state of the program. This third function is the epsilon greedy algorithm. So a random number from 0 to 1 is generated, and if it is less than epsilon, then it will choose the highest value action from the Q values. If not, it'll choose a random action. That's because you don't want it to always choose the highest value one. You want it to take a little bit of risk because then it can find a more optimal path. This fourth function just updates the location of the actor based on the action chosen. And then this last function actually finds the shortest path that the actor takes from where it starts to the goal. The training will likely change because I'll try to find optimal values for these training parameters that work best for the actual laser. And right here, instead of outputting the path that the actor will take, it will actually perform the actions on the motors.